Hello friends. Welcome to the Different Science channel. Do not forget to like, share, subscribe. You can also instantly be notified of my videos by clicking the bell next to the subscribe button. You can support me with the instructions in the description. If you're ready, let's start. Goons, damaging our eyes, is the most basic source of life. The energy that has been opened by spending 600 million tons of hydrogen in every second gives the world for a few billion years of life. When we look at the sky at night, just like our sun, we see the stars that emit intense energy and bring their lights hundreds or even thousands of light years away with the enormous energy of this energy. For example, Deneb is one of the very distant stars we can see with the naked eye, a supergiant at a distance of 2,600 light years. He has consumed all his hydrogen and is now delivering the light of burning helium with triple alpha reactions. In contrast to the general belief, stars do not burn their fuels, they combine atoms. It is thanks to the nuclear fusion reactions that we are trying to create in the world, as we can see the glow above us on summer nights at such long distances. Our current focus will be on how to create artificial nuclear fusion and use it on Earth and in the discovery of the universe. Before the 1920s, we had no idea how this enormous energy was exposed, how the stars were able to live like this. In 1920, Francis William Aston discovered that the energy equivalent to 4 hydrogen atoms was more than the energy equivalent of a helium atom. This meant that net energy will be released as hydrogen atoms combine to form helium. For the first time, we had an idea of fusion reactions in the stars, as Arthur Eddington, based on Aston's research, suggested that the atomic nuclei combined to produce energy and that the stars received power from it. What is a fusion and what is the difference? Fusion reactions, light elements tend to repel each other, called Coulomb power, overcome with strong nuclear force and create another atomic nucleus, sometimes called neutrons, and very high energy releases. In order for this powerful nuclear force, which is one of the 4 main forces of nature, to be superior to the electrical repulsion that keeps the atomic nuclei from each other, the nuclei must come close to each other by the effect of heat and/or pressure. While fission-based nuclear energy, which we use today, breaks down heavy elements such as uranium and converts them into different elements, fusion reactions occur thanks to the combination of light elements. Depending on the type of reaction, although the substance now varies, a long-term radioactive waste such as fission is not produced. For example, a deuterium-tritium reaction produces helium and a neutron with an energy value of 14.1 MeV. What we need to worry about is this neutron, and since this neutron will also be isolated, the only waste that emerges will be helium, which is quite useful. The nuclear fusion that gives us life has tremendous potential. Unfortunately, it is a joke that we use fossil fuels compared to fusion. Fossil fuels are extremely dirty, primitive and inadequate, far from efficiency. Even the fission-based nuclear energy used today generates millions of times more energy than fossil, while the first-generation commercial fusion reactors will produce 3 to 4 times this. For example, a 1 gigawatt coal plant will burn 1.5 to 2.5 million tons of coal annually, while an equivalent first-generation fusion plant will spend just a few hundred kilograms of fuel. While coal releases extremely toxic gases into the atmosphere, fusion reactions will not be a harmful residue. After all, this energy in the heart of the stars can solve all the energy needs on our planet. Creating star energy in the world under the influence of a huge amount of gravitational forces in the core of our Sun, 250 billion times the pressure and 15.7 million degrees Celsius temperature in the world creates a very suitable infrastructure for fusion. Here, fusion reactions continue within approximately 24% of the solar radius. While fusion continues as an ordinary event under such extreme conditions, we have not been able to make this event sustainable with our own technology in the world for more than 50 years. Fuel, which consists of various hydrogen isotopes (DD and DT), must be heated to 100 million degrees Celsius, and a dense and compressed environment must be created so that the atoms combine. Thus, ignition should be provided and fusion should become self-feeding. Electricity production from fusion currently, many of the R&D studies are on hydrogen isotope reactions that produce high-energy neutrons along with charged particles for technological convenience. Electricity generation also takes place thanks to these charged particles and neutrons. Thermal conversion, an enormous amount of heat is generated during fusion. We can convert it to electricity with steam turbines by conventional methods. 80% of the electricity in the world is produced in power plants using such steam turbines. This is a tried and specialized area. However, converting heat to electricity has only 33 to 50% efficiency. Direct conversion, it means producing electricity directly from charged particles in motion. In other words, there is no phase of generating electricity through a steam turbine by heating a coolant or gas, and it provides 90% efficiency and higher compared to the low efficiency of the thermal conversion. Reactions with low neutron production are required to make the most efficient use of direct conversion systems. Because neutrons are uncharged, we cannot use the energy they contain in direct transformation. As we will mention in the reaction types below, there are reactions with low neutron production, but they are very difficult to develop in the near future as their energy needs are very high. Net energy, fusion needs to feed on its own. The energy produced by fusion has to be more than the energy spent to bring it to the ignition state. Thus, fusion reactions both produce energy that feeds the environment in which ignition is created, and 3 to 4 times more energy is released than fission reactions. Fusion reactions were created countless times in experimental reactors. Even the news that we created the sun in his garage, which we heard from time to time, is also true. Fusion reactions can be created with simple devices called fusers. However, no more energy is produced than these reactions are spent. We know that it is possible to produce more with experimental results and formulas, but it takes a long time to turn this into a power generation system, as we have developed the necessary technology over time. As a result of more than 50 years of research, we were able to get the most positive news on this subject only by generating more energy in the NIF reactor in September 2013 than was spent for the first time. Steady-state power, reactions for electricity generation should be instantaneous in dynamic stability or short-term rapid pulses. The purpose of fusion research is to produce energy in a constant and continuous state in dynamic stability. Let's exemplify this issue with the currently operating JET reactor and the ITER and demo reactors that will be activated in the near future. JET 1982 present short-term fusion with 20 to 60 seconds pulse is possible. High-energy reactions take less than a second. ITER 2019, it is planned to generate 500 megawatts of electricity for 1,000 seconds in this experimental reactor, which will be completed in 2019. Demo 2033, this project, which aims to sustain the fusion reaction with dynamic stability, is expected to be connected to the power lines by 2040. Risks and safety. The DT deuterium-tritium and DD deuterium-deuterium reactions, which are currently the main research subjects, produce a high amount of neutrons, called neutron current. Isolation of neutron flow is one of the important engineering studies in fusion reactors. The isolated neutrons will also generate heat, and thermal conversion will be the main source of electricity generation. However, the insulating layer will become radioactive over time and will need to be replaced. Apart from that, they do not have risks, do not explode, do not leak, and in case of an accident, the system can be stopped by simply cutting off the power. Although the substance produced, it would be wrong to call the elements formed as a result of fusion reaction as waste because of the reaction type. They are generally useful elements such as helium and tritium, an isotope of hydrogen. Although tritium is a radioactive substance, it emits beta radiation that can be shielded easily and is a short-term product with a half-life of 12 years. Moreover, being a DT fusion fuel makes tritium highly valuable. Fusion reactions and fuel types. First, let's look at two types of reactions in the heart of our Sun. The PP proton-proton cycle, understanding the stars as a kind of reaction that is one of the main reactions in the heart of our Sun, but not very suitable for our use on Earth, as we mentioned in detail in our article series. Even the temperature in the core of our Sun is not enough for protons to overcome the Coulomb barrier in a classic way. However, as we began to understand quantum mechanics, we discovered that these protons combined through quantum tunneling. Brief summary: quantum tunneling, particles crossing any barrier in between and going somewhere they can't go with classical physics. The old classical laws of physics say that particles don't have the energy to cross barriers. However, quantum physics has shown us that particles can have both particle and wave properties. Thus, from time to time, there is a possibility to borrow energy from a proton environment and overcome the barrier between this energy. This phenomenon is seen in barriers of 1 to 3 nanometers or less. Let's go back to our fusion topic, which is easier to understand and explain without burning our brains anymore. The pp cycle is slow because it only works with quantum tunneling. Sometimes a billion years may be required for a single proton to have a fusion reaction with another proton. Another obstacle in front of protons reaching each other through tunneling is that they need weak nuclear force interaction, which is less likely. Despite these weak possibilities, this is the main reaction type in the Sun. Because there are trillion x trillion atoms, that the weak possibility can easily turn to high probability. As a result, 4 protons combine, a helium nucleus, alpha particle, some neutrino, and 26.73 MeV of energy is released. CNO, carbon nitrogen oxygen cycle. If the Sun was 1.5 times larger, this would be the main fuel cycle. In this reaction, also known as the carbon cycle, a heavy atom combines with helium in places, switching between carbon, nitrogen and oxygen isotopes and releasing 27.8 MeV energy during this process. While only 1 to 2% of the energy produced in the Sun comes from this cycle, the star of Sirius A shines with the energy of CNO cycle to a large extent. As you can imagine, CNO is a cycle that is not yet possible for our current fusion technology. B. The reactions focused on fusion research. DT, deuterium 2H, tritium 3H. Cycle. Now, we can talk about a cycle that we can use in the world and on which a lot of research and development is done. DT is the easiest type of reaction that needs the lowest energy. Let's take a look at the fuels. Deuterium is a fairly common isotope with about 30 grams per cubic meter of seawater. This hydrogen isotope, which is found abundantly in space, on other planets, satellites and comets, as we can use deuterium reserves on Earth for thousands of years in fusion reactions. Tritium is a radioactive hydrogen isotope with a half-life of about 12 years. It is not found in nature and is produced during the interaction of cosmic rays with our atmosphere. With our current technology, tritium is produced in normal nuclear reactors. In the near future, tritium production will be made by the neutrons released during fusion bombing the lithium element. Known lithium reserves in the world are sufficient for at least 1,000 years. Tritium production can also be done in DD cycles. DT reactions take place as follows: 2H plus 3H equals 4 He 3.517 MeV plus N 14.069 MeV. 20% of the energy released as a result of the reaction is 3.5 MeV helium isotope alpha particle and 80% is 14.1 MeV. DT is the most suitable reaction type for use in tokamak-type reactors. It is more intense compared to the DD reaction, which we will explain shortly, and is lower than DD with 13.6 keV energy, which is the peak of the reaction rate. Among its advantages, besides being clean and safe like other fusion reactions, the disadvantages of this cycle, which is technologically and engineeringly easy, are: as we wrote earlier, it requires the production of tritium, so a layer called lithium blanket will be bombarded with neutrons produced in the reactor and will produce tritium. This method also has different challenges. Another disadvantage is that 1/5 of the reaction's energy will remain in the plasma, since neutrons will carry 80% energy. This complicates the continuity of firing. DD, deuterium 2H cycle. This reaction, which uses only deuterium, is another research topic that stands out as it does not require any other fuel that is difficult to acquire. The DD reaction reaches the peak of the reaction rate required for sustainable firing, with energy of 15 keV. This is higher than DT and thus more challenging. This reaction yields two different products in equal proportions. 50%, 2H plus 2H equals 3H, tritium, 1.01 MeV, plus 1H, P plus 3.02 MeV, 50%, 2H plus 2H equals 3 He, 0.82 MeV, plus N, 2.45 MeV. Tritium and helium-3 produced as a result of the reaction will be recycled to increase the amount of charged particles and reduce the amount of neutrons. Namely, if the tritium formed as a result of the reaction can be collected, the neutron release that would otherwise occur will be quite low and the reactor D He 3 may continue the reaction. It can also be used in tritium-DT reactions, or it can be used in D He 3 reactions when it degrades and turns into helium-3. C. Neutronic reactions. The following types of reactions do not involve neutron release and are much more efficient, but their difficulty also increases in direct proportion. Their biggest advantage is that they do not require neutron shielding and enable direct energy conversion. D He 3 deuterium 2H helium-3 3 He. Cycle. In this reaction, deuterium and helium-3 isotopes rare in the world are combined. In order to explain how rare helium-3 is, we think it would be sufficient to illustrate that there are ideas for collecting this isotope from the Moon's surface and even from Jupiter. Helium-3 is also formed as a result of tritium undergoing beta decay. As we wrote for deuterium, tritium can be produced by obtaining deuterium from ice, which is already abundant in asteroids, comets, gas giants' rings and satellites, and by bombarding this deuterium with neutron. Another and the main challenge of this reaction is that 58 keV energy input is required for the reaction to reach the most efficient point. 2H plus 3 He equals 4 He 3.6 MeV, plus 1H P plus 14.7 MeV. This transformation can take place as a secondary reaction in DT reactors. However, since a reactor that will only perform the D He 3 reaction will mostly be based on stocks to be brought from abroad, it will not be economical to use at least on our planet. However, if we can find sufficient stock on the Moon, it may be indispensable for energy production on the Moon as our technology evolves and around gas giants. Of course, if we can overcome the problem of energy need to start the reaction. D He 3 is also a reaction that we can describe as cut out for fusion rockets, which we will talk about in the next section of our article. The low energy requirement compared to P11b and being a neutronic are great advantages. The P11b proton, boron 11 cycle P11b is a targeted reaction for the distant future, not possible now and in the near future. If a neutronic fusion is intended, sooner or later it will be the ultimate goal of fusion technology. The proton-boron reaction is the ultimate goal. Meanwhile, boron is the Bohr mine we know. 1H plus 11b equals 3x 4e plus 8.7 MeV. In this reaction, a proton combines with boron 11 to form carbon-12. Carbon-12 decays as 3 helium-4. Although this reaction looks like fission, helium-4 is one of the most stable isotopes in the universe. With much less neutron emissions than the D He 3 reaction, the P11b is almost completely clean. With 0.001% neutron release, only one neutron is produced per thousand reactions. In addition to having an aneutronic reaction efficiency, its fuel is also quite common and abundant. The only, and unfortunately big, drawback is that the reaction rate reaches its peak at 123 keV. That is, the required temperature is close to 1 billion degrees Celsius, which is 10 times higher than needed in a DD or DT reaction. Magnetic fields that will provide energy imprisonment must naturally be 500 times better. Polywell and dense plasma focus compression methods with more radical differences are considered for this reaction, which is outside the limits of the tokamak and laser-focused reactor models. D. Muon catalyzed fusion, cold fusion. Let's talk about muon first. A muon is 200 times heavier than an electron and decays to other particles within 2.2 milliseconds. If a muon is found around an atomic nucleus instead of an electron, its orbit will be 1/200th of the electron. The degraded muon weakens the Coulomb barrier, allowing fusion to take place at lower temperatures. It even lowers the required temperature so that the reaction can take place even at room temperature. So much so that some researchers cool and use fuel up to minus 270 degrees. Although it sounds good, of course there are problems, let's talk about them. Alpha sticking, helium, which we call alpha particle, contains 2 protons and 2 neutrons, so its charge is +2. The charge of the protons attracts the -1 charged muon to them, and under these conditions, the reaction does not occur when the muon decays after 2.2 milliseconds, as proton fusion will not occur. When we use boron-11, muon loses its effect to a large extent due to the electrons around the boron, so muon catalysis is useless in heavy atoms. In order to benefit from the muon catalysis method more effectively, a more efficient way of producing muon should be found. Currently, 6 GeV energy is required for the production of a muon. This energy is more than the energy released from a muon-incorporated fusion reaction. Making cold fusion reactors operating at room temperature is not economical for now unless there is an efficient method for muon production. But if an economical and simple method of muon production is developed, Mr. Fusion, which will run our homes and cars, can be real. See Back to the Future 2. Fusion reactors and R&D works. Topics such as fusion energy is 20 years away and fusion after 10 years have been decorating newspapers and news for almost 50 years. For some circles, this is now a source of humor. Yes, we cannot produce more energy with fusion yet more efficiently, but we can create fusion reactions. Research and development work is carried out in many fusion reactors in the European Union, America, Russia, Japan, China, Brazil, Canada and South Korea. The first fusion research was conducted in conjunction with the US and Soviet nuclear weapons research, and remained secret until the Atoms for Peace conference in Geneva in 1958. Although many nations have carried out fusion work on their own for many years, increasing research costs and the complexity of the devices used have required international cooperation. Today, there are research facilities and reactors that carry out their experiments with many different methods. Let's talk about methods and important R&D studies. Gravitational confinement fusion, GCF. What makes fusion reactions occur in the stars is gravitational imprisonment. We do not yet know a theoretical or practical way to artificially create it. The stars must be at least 75 Jupiter mass lower limit for fusion reactions to occur even in nature. Since we know that deuterium fusion can also occur in brown dwarfs with 13 Jupiter masses, and lithium fusion can happen in those with 65 Jupiter masses, we can only settle for gravitational imprisonment. Note, these reactions occur very rarely and in very small amounts in brown dwarfs. So it is never enough to warm and shine these objects. Magnetic confinement fusion (MCF). With this method, hundreds of cubic meters of fuel, preferably DT in many studies, are compressed into a much smaller area with magnetic fields. Magnetic fields are ideal for this because ions and electrons will follow magnetic fields because they are charged particles. The main purpose here is to prevent the particles from contacting the reactor walls and losing heat and slowing down. Any material that is not already protected by magnetic fields cannot withstand fusion temperatures. The donut-shaped reactor design, called toroid, is the most efficient for magnetic fields. In such reactors, plasma is trapped by magnetic fields following spiral paths. Below we will talk about the 3 main models of toroid-shaped reactors: tokamak, stellarator, reversed field pinch (RFP), and several other MCF models. Two-buckle tokamak is the most preferred and researched model in controlled thermonuclear fusion research. In these reactors, magnetic fields are produced by toroidal coils spaced equally around the reactor, and a helical direction of motion is given by the poloidal coils that cut them at right angles. This design was the product of Soviet scientists Igor Tamm and Andrei Sakharov in the 1950s. The biggest problem in tokamak reactors is to heat the plasma and bring the fusion reactions to the efficiency that will produce the energy to feed itself. This is possible at about 100 million degrees Celsius. With the current methods, ohmic heating, electric current heating technique, provides 20 to 30 million degrees Celsius temperature. For higher temperatures, plasma fuel is bombed with high-energy neutral atoms, magnetic compression is enhanced and radio waves are used. Heating provided by neutrons produced in DD and DT reactions is the main energy production method. The heat provided by these neutrons is insulated with ceramic coatings on the inner walls of the reactors. Separate layers of liquid helium or liquid nitrogen are available to protect electromagnets. Research is currently underway in about 30 experimental tokamak reactors operating in different countries. The biggest and most famous project, Joint European Torus (JET), has been one of the largest pieces of active research in England since 1984. The energy production record of this reactor is to obtain 16 megawatts fusion energy with 24 megawatts energy input in 1997. With a 5-year extension contract signed by the European Commission in 2014 and an appropriation of €283 million, scientists and engineers are preparing to set a new record. International Thermonuclear Experimental Reactor (ITER), which will be completed in 2019 with the knowledge and experience gained from the JET project, has turned into a mega-project with the participation of the European Union, India, Japan, Russia, China, America and South Korea. It is planned to produce 500 megawatts fusion energy with 50 megawatts energy input. The construction of the ITER complex started in France in 2013, and its construction fee has tripled the planned wage already, with a ceiling of $16 billion. This fee is quite close to the annual military spending of the Turkish armed forces. After completing in 2019, the first plasma experiments will start in 2020 and will continue with DT fusion experiments in 2027. Thus, ITER will end their conversations, fusion 10 years away, we hope. Demo plant, which will be completed in 2033 by following ITER, will also use the tokamak model. It will be equivalent to today's nuclear power plants with energy production between 2 to 4 gigawatts. In addition to these projects, South Korea realized the first plasma production in 2008 with the K-STAR project and is currently used as a test bed for ITER. The project named K-Demo, which is planned to be implemented in 2037 following K-STAR, will be developed in connection with Demo that will be completed in 2033. Stellarator, Starter, although they were popular in the 1950s and 60s, Stellarator models, which were developed as an alternative to tokamak reactors, were dismissed because the tokamak achieved better results, but they were revised due to the problems experienced with the tokamak in the 90s. Although Stellarator is structurally similar to tokamaka, it is quite unusual. The reactor models are generally in the form of a donut, curved and elongated to look like the number 8. Despite the design difficulty of stellators, its biggest advantage is that there is no need for toroidal current generation. In the helically symmetric experiment (HSX) project at the University of Wisconsin-Madison, the optimization of this design is dealt with. R&D studies are also carried out in the H1 project in Austria. RFP in tokamak reactors, magnetic fields in the toroidal direction are more intense than in the poloidal direction, whereas in the reversed field pinch, magnetic fields are equally strong in both directions. The direction of the toroidal current is the opposite of the clap. The strength of the magnetic fields can be as low as 1 in 10 of the buckle. Thus, precise and expensive superconducting magnets are not needed. The current flowing through the plasma is more intense. Despite these advantages, their disadvantages are strong. Plasma trap is only as efficient as 1% of the knockers. The outer shell must be conductive and exposed to a high amount of electric current for magnetic field production. Global tokamak, spherical tokamak, as the name suggests, it is a spherical model of the tokamak design. Experimental global knocker reactors are available in Russia, America and the UK. However, since the first time they were put forward coincided with a period in which fusion research in America was financially interrupted, it did not attract as much attention as the traditional knocker and a generation remained behind them. It is a more practical, inexpensive and high plasma stability model, moreover, smaller. The fact that it does not include electromagnets due to its small size reduces the costs. However, traditional magnets are less powerful. In addition, lower plasma pressure is also a problem. Also, since there is no magnetic shielding, the parts exposed directly to excessively hot plasma may need to be replaced frequently. Magnetic mirror prison. In this system, plasma is compressed between magnetic fields called diamagnetic cusp, produced by two magnetic mirrors. Magnetic power constantly changes direction and intensity, compressing the plasma to the midpoint where fusion will occur. According to the press release of Lockheed Martin, the compact fusion reactor project, which uses the magnetic mirror model they call high beta fusion reactor, will start mass production after 5 years and will provide 100 megawatts of electricity with a container-size reactors. According to the company's presentation, their designs will be much smaller, cheaper and more efficient than ITER and similar mallets. With a reactor of the same size as ITER, it will be able to produce 10 times the electricity of ITER. From supplying electricity to cities, there will be a wide range of uses as power source for manned space flights. The project started in 2010 and was announced in November 2014. If we think that Lockheed Martin is not a company that violates the thermodynamic laws like ERC and makes ambiguous inventions, it is better to understand the seriousness of its announcements. Indeed, if this project does what it promises, it will not only solve the energy problem of the Earth, it can turn it into the #1 economic power, the world's largest defense industry company. The reactors, on the other hand, can displace oil companies and enable fusion rockets that we cannot use in spacecraft today. Inertial confinement fusion (ICF). With this method, the fuel is heated and compressed with high-energy lasers. As you can see in the figure below, the heated outer layer expands outward, compressing the fuel by sending a shock wave inside. If this compression is strong enough, fusion reactions occur. These reactions can also put the rest of the fuel into fusion reactions. Such fuel parts contain about 10 milligrams of fuel, and that 10 milligrams of fuel releases the same amount of energy as a barrel of oil. 159 million milligrams of oil equals 10 milligrams of DT. ICF is a newer field than magnetic prison, and it was proposed in the 1970s. The reactor models have grown and developed since the years it was proposed. The most important example of this method today is the reactor in the National Ignition Facility (NIF) in the USA. In the application of this method, Rayleigh-Taylor instability arising from the power inequality between lasers sent to the target today, even if many problems such as the level of energy sent to the target, shock waves and symmetry of the collapsing fuel and overheating of the fuel without reaching the maximum density have been more or less overcome in the past decades. Is the most important problem. NIF, the largest representative of this method, was completed in 2009 and started experiments in 2010. Although the aim of creating an energy focus of 500 terawatts was achieved in 2012 in the NIF reactor by intersecting the 192 high-energy laser at one point, ignition could not be achieved. However, with the release of 5 × 10^15 neutrons on September 29, 2013, 75% more neutrons were produced than previous experiments. Alpha heating, the release of helium isotopes from fusion, was achieved, and the reaction broke a historical record by producing more energy than wasted for firing. However, some of the energy of the lasers used for this reaction is absorbed by the outer layer called holorum that holds the fuel. That is, higher energy was used to fire the lasers, but the absorbed energy reaching the fuel was lower. Fuel released more fusion energy than this absorbed energy. Today, NIF focuses on material research instead of fusion with the deduction of the allowance. Apart from NIF, the Laser Megajoule facility in France started ICF experiments in October 2014. In Japan, Osaka University has been carrying out ICF tests since 1983 with the Gecko 12 ICF laser device. Z-pinch, zeta pinch, Z-pinch is a Lorentz power application. It is a combination of both MCF and ICF methods. In this method, a magnetic field compressing the plasma is created by passing an electric current through the plasma. Z, who gave his name Z-pinch, tells the direction of this electric current in the three-dimensional plane. External magnetic fields are also used to create this electric current. So there is no physical contact. The first studies on this method started in England after the Second World War. Z-pulsed power facility, known today as the Z-machine in the USA, is the world's largest X-ray generator, which was used for material testing until 1996. The device in Sandia National Laboratories is used in many different areas from modeling nuclear weapons to fusion-oriented research after 1996. Here, Z-pinch tests are carried out with the magneto-inertial fusion method and DD fuel. This method creates a Z-pinch magnetic field with 100 nanosecond electrical pulses and applies pressure to the cylindrical HOHS containing fuel and heats a laser fuel before it collapses. In 2014, after the last tests with 10 Tesla power magnetic field and 2.5 kJ laser, TESIs started updating studies until 2018. In 2018, 30 Tesla magnetic fields are fired with the help of 8 kJ laser and DT fuel, and it is expected to produce 300 megawatts of fusion energy by spending fuel lumps every 10 seconds. While T-pinch method, which is similar to Z-pinchon, sends electric current in theta direction, screw pinch applies electric current in both theta and zeta directions. Inertial electrostatic compression, inertial electrostatic confinement (IEC) fuser, a fusion device that you can make in your garage. Electrostatic inertia imprisonment method creates fusion reactions by heating ions with electric fields. They are used for neutron generator instead of generating electricity. Polywell, it is very similar to fuser. In this model, a negative voltage is created with a magnetic field through which electrons are captured via electromagnets, and this attracts positively charged ions. As ions accelerate towards the negatively charged center, their kinetic energies increase and fusion reactions may occur when they collide at the center. As an intellectual father, Robert Bussard, as well as fusion research, conducted research on nuclear thermal rockets and his own named Bussard ramjets. The research conducted by Bussard's Energy Matter Conversion Corporation (EMC2) company, funded by the U.S. Armed Forces, continues to be known today, after being confidential until 2006. Many university laboratories are also working on polywell reactors. Just like today's nuclear power plants, fusion energy will reduce the damage to the environment, acid rains, and greenhouse effects. Sooner or later, although fusion alone will meet all energy needs and end fossil fuel use, our children and grandchildren will witness a long and difficult transition period by that time. The cheap and abundant energy it will provide will not only illuminate the cities but also support scientific researches requiring high energy, and can be used as an energy source and propellant after sufficient optimization in space. As the technology evolves, the DT and DD fuel cycles will be replaced by the DHE3 and P11B cycles that do not produce neutrons, and will raise energy production until more advanced technologies are produced. Now that we have examined the current and future location of fusion in the world, let's jump into the nearest rocket and go into orbit. In the next part of our article series, we will examine our fusion rocket and fusion reactor ship waiting for us in orbit. Thanks for watching.